I'm Tim Ventura, and we're joined today by Dr. Honghai Song, the CEO and founder at Canyon Magnet Energy, a superconductor startup working to facilitate high-temperature superconductor magnet scale-up and large-volume cable production for limitless fusion energy and affordable healthcare. Dr. Song has a PhD in electrical engineering and applied superconductivity from Florida State University, along with extensive experience in the research industry. Before his current role at Canyon Magnet Energy, his career included work as a research scientist and professor at Stony Brook University, magnet engineering consultant at Mevion Medical Systems, physicist at Brookhaven National Labs, team lead and magnet scientist at FRIB Michigan, project lead at SuperPower Inc, as well as post-doctoral work at GE Global Research. So Honghai, welcome, sir. It is a pleasure and an honor to have you with us today.
Thank you so much, Tim. It's a great honor to join this discussion. Thank you so much.
Well, today we are talking about high temperature superconductors and fusion energy. And this is, I mean, as the intro shows, this is absolutely an area of specialization for you. There has been so much movement in both of these fields over the last couple of years, especially in superconductors this year. So I'm really excited to have you with us. I want to start out with the basics, though. What inspired you to start a commercial superconductor company? What kind of superconductors do you specialize in? And what makes your company's product different than other superconductors out there?
Yeah, sure. As you mentioned that, so I've been working on the field for like post-degree 13 years. So I did my PhD back in 2010. It's like 13 years ago. So I've been working in national labs and also the universities, some of the research laboratories. So I feel that at this moment, there is like a big technical drive on the clean tech technology side, let's say the fusion energy. So fusion energy has been heavily invested by both the federal government and also the private sector. So we are looking at like $6 billion in total. So that basically drive the superconductor, to like reaching the long length production. Right now, we're talking about like 10,000 kilometers per year, the volume production. The second part, the price actually is going down. So we are achieving like 50% of the like cost reduction. So as we have more HTS manufacturers, join the field, like the Maddox in Texas and also HTS manufacturer in Santa Barbara. So we're seeing more cost reduction in the coming years. So let's say we achieve another 50%. So that's like really the fourth of the cost we talked about, like 5 years ago. So it's really the volume production of HTS wire and also the cost reduction, kind of creating the opportunity for both the fusion field, but also for other field like medical field, MRI, proton therapy, and also for some of the military application.
Okay. Well, and that's wonderful. Actually, you're answering a bunch of the questions I had written down there. So if I trip over my tongue later, it is because I am dancing around in my questions list. But yeah, that I was going to ask that. So it sounds like the cost is starting to drop, production is going up, and then that's enabling applications in fusion, right? Because those powerful magnetic fields are absolutely beneficial for fusion reactors, as well as things like MRIs. And now I wanted to ask, this is off my topics list, but I know that MRIs use these. Are there other medical applications that use them?
Yes, MR will be definitely one of them. MR field is pretty large. So we're talking about like, a few thousand MR units, out into the hospitals, medical practices. So every year you talk about a few hundred units, out into the field. So it's definitely big market. We actually have some simple analysis on that. So we're looking at like $10 billion like market in project in 2028, like 5 years from now. So one of them would be, in addition to MRI, there would be a proton therapy. So basically, they have like a digitized cyclotron machine, and then it can be one of the type. And then they produce the beam through a dipole magnet, quadrupole magnet for particle bending, and also the focus defocusing, and eventually they will produce a beam, and then the beam will, kind of like apply to the patient on a specific area, basically to kill the tumor, and in the having the benefits which like the other radiation material does not have. Basically, it can hit on the specific material that has a lot of radiation to the neighboring area. So let's say you have if someone has like a tumor in the brain, they can kind of like cure a specific area without damaging the neighboring tissues. Yeah.
Ah, okay. Okay.
Yeah.
Well, and one of the things that's important to keep in mind, and the reason I mentioned the medical applications, fusion would also benefit from this. But when people go into the doctor's office, right, and they have those MRI scans, or as you mentioned, proton beam therapy, the costs on those have traditionally been very high, right? Even if the insurance company picks that up, somebody is paying for that. And the reason is they have to amortize out the cost of that equipment. So by reducing the cost of the superconductors and improving the production techniques, you're able to drop those costs, which just benefits everyone overall. Well, so for the audience sake, I want to do a couple of definitions here. A high temperature superconductor has a critical temperature above 77 degrees Kelvin, which is around negative 321 Fahrenheit, if I remember correctly. That's the boiling point of liquid nitrogen. So the one that
Tim, quick question here. Basically, the critical temperature is about 90 Kelvin, but it can operate at 77 Kelvin and also lower temperature.
Ah, okay. Well, thank you for correcting me. Thank you. I work by Wikipedia and other research notes, and sometimes they get it wrong. So if they get it wrong, I get it wrong. But so the one, and I'll be a little more hesitant here, but the superconductor most people are familiar with, at least I'm most familiar with, is the YBCO superconductor that's used in science demonstrations, right? When people go out and buy one to demo it for the kids, and they show them flux pinning and things like that. A lot of the time, those are YBCO superconductors. But there are lots of chemical compositions. I'm not going to get into type 1 and type 2 today, but Wikipedia says that as a comparison, bismuth, strontium, calcium, copper oxide, or BSCCO is an alternative, and it's actually more practical for a lot of high temperature superconductor apps because it doesn't contain rare earths. So what are some of the best formulations? What are some of the best chemistries that are actually used in industry right now?
Sure. That's definitely a good question. So HTS, was discovered back in 1986 in that time. And then there is a lot of interest in the bulk superconductor. So in the bulk like a pellet. And then there is like about 10 years, people working on the first generation of HTS, which is the one you mentioned, like bismuth 2223. And then after that, there is like, since like early 2000, people have started working on the second generation, which is the ReBCO. So ReBCO compared, generation 2 compared to generation 1, basically it has two benefit technical advantage. One is the mechanical properties is better. So when you do the coil winding, right, you apply tension on the coil so that you have a compact coil winding pack. So ReBCO conductor may allow you apply high tension. Bismuth 2223 is kind of brittle because its material is made of silver. When you apply the high tension, the filament inside it may get it is brittle and it become like broken. So basically, when you're losing a certain percentage of the filament, inside the superconducting matrix, you're losing basically losing the critical current density, which is the current carrying capability. The second part, mechanical is one thing. The second part is the critical current density. So the ReBCO as a generation 2, which has a very high in-field current density. In-field means usually when you build a magnet, right? So the magnet itself has a peak magnetic, let's say at 10 Tesla or 20 Tesla. So let's say at 20 Tesla, ReBCO can provide outstanding, very high current density compared to maybe, let's say 20 Kelvin, 20 Tesla, it may be like a few times more than BCO 2223.
Okay. Well, and I
Yeah.
appreciate you sharing that. I want to drop in a plug for Canyon Magnet Energy again, because I am so appreciative of you sharing your time with us. I'm not being paid. I am not doing a paid endorsement here of any kind. I just appreciate you sharing it with us. And this is your area of specialization. This is something that your company makes. So let me drop a plug there for Canyon Magnet Energy, and I will put
Okay.
links in the show notes to that as
Okay.
well. So all of these superconductors still require cryogenic cooling, right?
Yeah. Totally.
Okay.
Totally. Yeah. So all the superconductors, as we talked about before, superconductor has a three-phase definition, right? So it has a upper critical temperature. So let's say if you start the superconductor transition at a certain temperature, like ReBCO will be at around 90 Kelvin. Physicist 2.3 has relatively higher TC, let's say 120 Kelvin. So although it would need to be run at a lower temperature. But the second thing, like compared to the TC, the critical temperature, we need to pick like what is the optimal operating temperature for the superconductor. So usually there is like empirical like conclusion saying that we need to choose like a half of the TC at the optimal like point. But the real basically to picking the optimal temperature is part of the real engineering design. Usually it's like for ReBCO, we pick at 20 Kelvin for the 20 Tesla magnetic field. If we're designing a higher, let's say a smaller field, let's say 5 Tesla compared to 20 Tesla, we build 5 Tesla magnetic field, a solenoid. And then we may allow to have a higher temperature because the lower field, you may have a higher current density. One thing I forgot to mention that. So the critical current density is magnetic field dependent. Right. So the field, when the field is getting higher, and then your critical current density is become like lower and lower.
Ah, okay.
Yeah.
Well, and the reason I'd mentioned that was,
Yeah.
to me, all of this feeds into the distinction between basic science, right? And
Yeah.
in this case, that would be the chemistry and this pursuit of room temperature superconductors that we'll get into in a moment, versus the engineering of it, right? And you talked about brittleness and materials and
Yeah.
commercialization. And so your company is on the commercial production side of it, but it sounds like that is where the advances are happening right now. The basic
Correct.
science for this, it sounds like, is relatively stable at the moment, even though things are moving forward on the research front. So really the focus is on increasing production, increasing the workability of these so that they can be wound more easily and effectively with less damage, as well as basically just producing them for lower cost.
Yeah, exactly. So actually, one thing I want to mention that we actually working with HTS manufacturer. So out of the field, we have like 7 or 8 HTS manufacturer. So we have SuperPower in US, and also Maddox in Texas, HTS in Santa Barbara, and also we have Fujikura in Japan, Faraday factory in Japan right now. Yeah. So we basically purchase an HTS wire from them, and then but we cable them into a specific pattern. Let's say we may make like stack cable, or maybe design into a specific pattern, which was really determined by the requirements. Either going to be carry like 20,000 amps, or maybe like 2,000 amps, or maybe sometimes we go very high current, like 65,000 amps. So that current would decide, what kind of cable would be designed and manufactured. You're right. The second part, we are going to take responsibility is to do the long length production. So we see that. Actually, I probably forgot to answer one of the question you asked, why we created the company. So we create companies to basically to be part of the fusion ecosystem, and then as a provider for long length HTS cable and also for the coil component. So if a fusion company need a HTS like complete solution, so we can provide the HTS magnet system as well, like SuperPower power supplies and also control system.
Okay. Well, let me touch on room temperature superconductors. The big one that I think most people heard about, right? This is only about 2 months ago, was LK99. We'll call that a room temperature superconductor candidate, and it appears to have been a bust. A lot of people got excited. I was very excited. People were pinging me through email. They're LK99. I actually had colleagues who were attempting to synthesize it, and they did. They were successful. They synthesized small amounts of that.
Yeah,
And I put that in my questions as well, because that was the learning experience for all of us.
yeah,
So to quickly read through what we saw, the news headlines were, if people can kind of, go back in their minds, they probably saw photos of tiny samples hovering over a magnet, exhibiting what's called the Meissner effect, doing it at room temperature, right?
yeah,
And that's because superconductors exhibit this perfect diamagnetism, and so they'll hover
yeah,
over a magnet. Well,
yeah,
it turns out that LK99 was not superconducting, but it is a very strong diamagnet.
that
And
magnet, yeah.
so it exhibited that property without the actual Meissner effect. But what
Hmm.
was interesting about that, the learning experience for me was, when friends and colleagues went to synthesize that,
Hmm.
they had to grow crystals of it. The crystal yields were small.
Yeah,
There is a time to grow those crystals, and so if they're under pressure, right? Like, okay, we need to do this in a week or 2 weeks. The crystals come out smaller. You have to
yeah,
separate them from a much larger substrate that isn't superconducting,
yeah.
and it turns out to be very difficult to create, identify, and test. I was very surprised.
Yeah, yeah, yeah. Yeah, definitely LK99 is very interesting. I think I actually pay attention to that also. So I try to read papers from archive from different groups. Um, so since there was some like reported like HTS, room temperature superconductor before, so I kind of like really in the mutual position. I like to see new breakthrough, but also I try to keep myself, calm down, but not too excited about it. So um, I think the conclusion, like the material itself is diamagnetic, as you mentioned. Uh, the the main feature to give the conclusion is because it cannot achieve a complete levitation. So usually for bulk superconductor like ReBCO, we can cool down to a certain temperature and then we can place above the permanent magnet. It can stably levitate there for like forever, basically, if you can cool the temperature, maintain temperature for a long time. So for this magnet, actually, I watched the videos from the website. So the small pellet, right, from a certain group, you can see that there is always like one side kind of touching the permanent magnet surface, even though it's a kind of like partially floated. So based on that levitation, I kind of conclude that that is not superconductor. Yeah, I mean later on, in a science magnetic field, a science field, basically, people doing a lot of verifications, right? If one group report, I'm achieving this room temperature superconductors, there need to be like like second, third groups to verify that. If the verification is made and successful, so that would be a successful claim. Yeah.
Yeah. Yeah. Well, the only reason I put that out there is just to remind the audience, because I'm sure you already know this, but just to
Yeah.
remind the audience that, real science is messy. It's not always precise, and it requires
Yeah.
a heck of a lot of work and a
Yeah.
ton of dedication and effort, right? And so,
Totally. Totally.
people see papers come out, and they'll see scientists make, claims or make hypothesis, and they think, oh, okay, well, this person is just working on a paper. In most of these cases, especially in this case, they're not. This is hard work, and it requires diligence and effort, and that not only
Totally.
applies to superconductors, but traditional, I mean, all electronics, every
Yeah.
product that we use has this that goes into it. Now,
Yeah.
if it's okay, I want to get into fusion. I love
Sure.
fusion. I have been actually doing interviews on fusion going back 20 years. And they've been saying fusion is 20 years away for the last 50. So,
That's right.
it's always 20 years away. And in my first
Yeah.
interviews, they were saying that. In your own background, you've worked with stellarators. So
Yeah.
let me start there. Can you tell me how those are different than the tokamak designs that we've seen in the news?
Sure. Sure. Yeah. Tokamak basically it has toroidal coil, um, and also the polarical coil. So that they combine the both, they will produce a path for the plasma, a helical path. And stellar on the other side, basically, it's kind of made of a lot of like twisted coils to kind of for the plasma pass, basically. The main difference, I guess, is really the structure. So the tokamak has a simpler structure, but it needs like plasma current to keep running. It's running at the pulse mode. It's actually become challenging for even for the material itself, and also from the maintenance point of view, you need a more frequent like maintenance material replacement. So stellar on the other side is up in a static mode, so it'd be easier in operation, less maintenance requirements. So that one definitely has a technical advantage. But at the same time, stellar, I mean, their twisted coil is quite complex. So if you look at W7X in Germany, actually I read a lot of papers on that project. So in the magnet fabrication, they have contract like 4 to 5 magnet companies. They are making low time superconducting magnets. And they also need to prepare for the possible delay because one vendor is running late, and they need to have a backup company to fill that position to make sure that their project will be going on time. Yeah. So basically, back to your question, yeah. So tokamak is easy to build. I think recently Proxima Fusion CEO Francisco has mentioned that it's more like a pilot helicopter. You have to keep like spinning and then make sure that the tokamak is running functionally. But stellar is more like airplane. So once it's fly in the air,
okay.
it will fly by itself in a very static state. But to build such a stellar system is more challenging. And at the same time, I want to say that from our company point of view, that's where we can make more contribution. So we can start from a design cable to meet the magnet requirements, and then we can build some prototypes to validate the cable design, eventually pave the road, to the full fusion magnet system.
Well, and I think it's important to point out that in your own background, you have extensive experience in the fusion research industry. And so really the Canyon Magnet Energy is kind of a crossover between the two. You're using your experience and knowledge in fusion, as part of the cable creation company.
Yeah.
So again, just for the audience, and I think most people are familiar with this, but maybe the best way that I could describe today's fusion reactors is you have basically hydrogen isotopes in gas that are circulating inside of an enclosed chamber, right? And the reactions occur in there, and that gas, that plasma, can't be allowed to touch the walls of the chamber, from what I've read. And so the magnets are used for that, right? That's at least part of it, is you have to contain that plasma, because when it touches the chamber walls, it immediately cools off and your reaction is lost. Is that kind of the primary use of those?
Yes, totally. So the magnet basically is to utilize, kind of produce the magnetic field to contain the plasma. So the plasma can flow, along the designed magnetic path. So it does not colliding into your the wall, right? The inside the plasma surface. Yeah.
Ah,
Yeah,
okay.
totally. Yeah.
Now, one thing that's news to me, and this should have been obvious, but I did an interview with a fellow who did fusion research years ago, and he said another aspect of this is because it's producing radiation, you get materials degradation. Is that something that's kind of a challenge with superconductors? Do you have to worry about, like neutrons from these reactions or anything along those lines coming out and damaging the coils? Because what he had said was, and I believe he was talking about GE Atomic research. He'd said that they actually had to replace the walls of the chamber periodically just because of damage from the radiation.
Yeah, that's a good point. There is actually a fusion material kind of research workshop, but I will kind of like scroll back maybe to HTS materials. So in a reactor, so the materials or the magnet, right, will be exposed to the neutron. So one of the main research, actually important topic is to study, how will the neutron affect the superconducting property. So there is ongoing research on that. Basically, we can apply different dose or amount of radiation into the superconductors. At the same time, we can measure the critical current density of the superconductors and then say at what level of the neutron radiation may damage the superconducting, let's say to a certain threshold, maybe 5% or 1%. And then with that data, and then we can come back and design a blanket system which can block some of the radiation from the superconducting layer.
Ah, okay. Well, I also wanted to touch on because tokamaks are large. Stellarators are large designs, right?
Yeah.
And that makes a lot of sense for these big commercial systems. But I did an interview back in 2007, I believe, with Dr. Robert Bussard, and he created the Polywell fusion reactor. And in his case, he was one of the directors of I believe it was the AEC back in the 1970s. And he got into mobile fusion systems. That became his passion. He did a lot of work for the US Navy. And the Polywell was similar to a tabletop inertial electrostatic or IEC design, except that in his case, he was using inertial magnetic confinement. Do you think that advances in superconductors, again, the production increases, the workability increases, things like you're working with, do you think that those could be used in smaller non-tokamak designs like this?
Yeah, totally. Actually, there are like two things to talk about this. One thing is like the HTS magnet will be used in tokamak and stellarator, but not limited to that. So actually, we are working with one of the fusion company. They actually need like solenoid type of HTS magnet. So HTS magnet, because it produces a high field, also the in-field current density is higher. So the magnet itself can be much smaller, much compact. So it can be easier to fit into the overall system. Yeah, definitely. HTS magnet, we will have a lot of potential for the fusion system. Yeah.
Well, and the reason I ask about that is from what I have seen, I guess in my own opinion, fusion
Yeah.
seems to be the end goal of nuclear. And, I have a good friend, Oscar, who posts on LinkedIn almost on a daily basis about nuclear energy. And I think that everything that he says is correct, but even in his case, he is very pro fusion, right? So it seems like the work that you're doing today is helping to benefit the fusion world of tomorrow, which will basically take the advantages of nuclear and hopefully scale those by an order of magnitude. I guess what I was wondering was like, because again, these materials, the cost, the workability, all of those things are improving and increasing. From
Right.
what I understand, fusion, I believe tokamaks or stellarators, one of the two,
Oh, you take
just
some
hit
time.
peak fusion for something like a second. I think they were able to do a pulse for a second and keep it stable.
Yeah.
And so I'm wondering how these improvements might help, move this all forward.
Yeah, I think that's definitely a good question. So we created companies try to kind of start to adding efforts in the field. So we will first definitely working from the superconducting side. So we will optimize the cable design and then for a better HTS magnet system. Second things, as you mentioned, it will take some time, 3 years, 5 years down the road. We will definitely keep our mind open to the new design from tokamak side, stellarator side, and then to support their design. If they have some new design, new requirements, we will absorb it into our design. Actually, we have some collaborators in the field. Because fusion company are actually our customers, so we'll keep constant conversation with them to make sure that we understand their requirements, their needs, and then to help them build the fusion magnet in their prototype machine or maybe in the first like production machine or power plant. And this kind of like our like mission one. So mission two is in the future when they build a successful like fusion reactor, and then they want to build a second one, third one in different location, New York or LA, or maybe somewhere maybe Texas, and then that's where we can play like more important kind of roles to produce the more HTS magnets or cables for them. At that time, we will be more like a tier 2 supplier company compared to tier 1 like fusion company. It's more like a, Ford, GM, when they're doing the automotive, production, they also need a second tire providers for, tires, for axles, and also for, even motors. Yeah.
Ah, okay. Well, and another application that I want to mention is space propulsion. I used to attend the ISNPS STAFE conference, and I saw many designs for fusion drive spacecraft. And the idea there is that you could reach Mars in weeks rather than years. I mean, the advantages of torch drives, right? I believe they've been described in science fiction shows like The Expanse. I believe those are primarily torch ships that are used there. Those were all fusion drive ships. I understand that fusion systems are easier to design and control for space propulsion than reactors here on Earth. Do you see a future for superconductors in that area as well?
Yeah, totally. Actually, for space, there may be like two main applications. One is the one you talk about, like for the rocket positioning orientation with the plasma system. Basically, if you be part of the plasma produce and control system, that's first one. The second one is really actually is for we can build a electromagnetic launch machine, on the ground, so that we can send a rocket into space that can kind of finish in the first step. So in both cases, so the application environment will be different. For the one, in the space, we need to think about like how can we get the cooling power? How can we to power the cryocooler, or maybe we use a different kind of cryogenic system. So that's one thing. The second thing on the Earth, right? When we are doing the electromagnetic launching, I think the challenge is really how to design a system which can accelerate your vehicles in a very fast speed. So that will including both the levitation, like vertically, and also the guidance, from the two sides. It does not collide into the wall, and also give enough propulsion and to send it out in a very high speed.
Yeah, yeah, and actually that second system, I just seen an article on that. There are a couple of different designs there. One of them almost reminds me of the Gyrotron, that amusement park ride, right? Where
Yeah,
it's a big wheel and it spins things up to speed and then
yeah,
lets it go. And that would obviously be for payloads. You would kill any astronaut or at least make them incredibly sick. But
yeah,
and then others, I think older designs have been basically like kind of like a rail gun, right? Linear rail, where it just
yes,
literally you have a big electromagnetic launcher, like they used to get aircraft off
yeah,
aircraft carrier decks, except that it would go fast enough that hopefully you could get something into orbit with it. So both of
yeah,
those, if you could produce fusion power, and then solve the energy release issues, because you'd have to release that very rapidly, you could use that to loft things into space, and that would reduce the cost of space access.
totally, totally.
Well, Honghai, let me thank you so much for your time today. It has been a pleasure and an honor having you with us. Again, I'm going to urge people to check out Canyon Magnet Systems, and I'll put a link in there. They can learn more about what you do. Hopefully, they can come up to speed on superconducting wire and fusion applications as well. Both of these are incredibly exciting areas, and there is a lot of movement forward in them. So, let me close by asking, what comes next for you? What do you see coming up in the next few months for your company as well as for superconductors in general?
Yeah, that's a good question. So for us, we're working on fundraising. So we actually have secured white investors. So we'll build HTS cabling facility, and also same time we build a coil winding facility, so that we can at least start with some small scale cable production and also coil production to satisfy our initial customers. In the long term, actually, we're looking at some of the niche field, like in the medical application, like the proton therapy we talk about, and also some of the compact MR system. That may take us 2 or 3 years. For in the longer term, we also know that the fusion will take longer time. So we'll work on a more complex HTS cables design, So we work on simulation, and then we do some prototyping, testing, and then to make sure that the HTS cables is validated, is tested, ready for the full HTS magnet system. So in 5 to 10 years, we hope to become a full HTS magnet system provider. So we can provide whole magnet system, including the cryostat, the power supply, control system, and then to support the fusion company, and then to make the fusion a reality on Earth.
Yeah, it is so exciting. It is so exciting. Thank you again so much for your time today, sir.
Thank you a lot, team. Thank you so much. I hope to have more conversation with you all in the future.